Yes, we'll discuss now how to find oblique asymptotes. So we have seen how to find asymptotes parallel to x-axis, y-axis. Now we'll see how to find oblique asymptotes. That means asymptotes which are not parallel to x or y-axis. Now generally we have to do this in case of implicit relations. The equation which can be expressed in this form f of x y is 0. So see, to find oblique asymptotes, first we express the equation in the implicit form, in the form f of x comma y is 0. In simple words, we bring all terms in the equation on the left hand side of the equation. Then we find the highest degree terms in the equation. We find the terms which of which the degree is the highest. Label it as phi suffix nm, phi nm, phi suffix nm. And in that we put x is 1 and y is equal to m. And this n, remember, represents the degree of this term. So suppose the highest degree term is, say, suppose x raised to 4 plus y raised to 4. Highest degree term will be of degree 4, then n will become 4. In that case, we label this as phi 4m. So see, we find what is the highest degree term. We label it as phi nm, where n will be the degree of that term, and in that term we put x is 1, y is m. How this is to be done? I'll show you an example, don't worry. Then next step, find the term with degree n minus 1. So if the highest degree term is of degree n, then we identify the term of degree n minus 1 in the given equation and label it as phi n minus 1 m. And again in that we put x is 1, y is m. Then we solve this equation, phi nm is equal to 0. So phi nm, remember, represents the highest degree term in the given equation, in which we have substituted x is 1, y is m. That equation we equate with 0. That term we equate with 0. Solving that equation, we'll get the value of m. Then to find c, we use the formula c is equal to phi n minus 1 m upon phi dash nm, where that phi dash nm is the derivative of this phi nm. We'll get the value of c from this. Now the equation of oblique asymptote is given by y is mx plus c. So find slope. Solving this equation, phi nm is equal to 0, where n represents the degree of the highest degree term in the equation. See, we find using this formula, and then equation of oblique asymptote is given by this formula, y is mx plus c. So m represents the slope of that oblique asymptote and c represents the y-intercept of that oblique asymptote. How this is to be done, see, we'll see in an example itself. So consider this example, x cube plus y cube is 3axy. We'll see how to find oblique asymptote for this kind of equation. So see, the given equation, first of all, we'll bring all terms on the left hand side. We bring the equation in this form, f of x comma y is equal to 0. We express the equation in implicit form. We express it in the form f of x comma y is 0. Or in simple words, we'll bring all terms in the equation on the LHS. Now identify degree of each term. See, x cube, we know degree is 3, y cube, degree is 3, minus 3axy, degree is 2, remember, 3a is a constant, and x into y, see, it is x raised to 1 into y raised to 1. Whenever it is multiplication of terms, we add the powers to find the degree. So here degree of this term 3xy is 2. So now here we can see that the highest degree term in this equation is x cube plus y cube. Degree of these two terms is 3. We label it as phi nm. So phi nm in this case is phi 3m. Degree of these two terms is 3. So phi 3m is x cube plus y cube. So see, we saw that in the given equation there are two terms with degree 3, and that is the highest degree term, or these are the highest degree terms in the given equation. So there is no term like x raised to 4. There is no term with degree more than 3. These two terms become the highest degree term. We label it as phi nm or phi 3m. Phi 3 because that n is 3, degree is 3, is equal to x cube plus y cube. In this we put x is 1, y is m. We get phi 3m is 1 plus m cube. And now the highest degree term is of degree 2, and the term with degree less, say if n is 3, we know n minus 1 will be 2. So, and the term with degree 2 is 3axy. We label it as phi 2m is minus 3axy. We take it along with this sign, minus 3axy. So see, phi 3m was the highest degree term, and phi n minus 1 is the term with degree of n minus 1. So here n is 3, n minus 1, notice it is 2. Suppose if there is no term with degree 2, then we'll take phi to m as 0 directly. इसमें देखिए कि x cube plus y cube का term है, there is a term of x cube plus y cube which was the highest degree term, and then we label it as phi 3m. The next term that we have to take is phi 2m. We have to take a term of which degree is 2. Here 3xy is a term of degree 2. If that term was not there, there was no term of degree 2, then we will have to take it as 0. Now, yes, in phi 2m, so we know phi 2m in this case minus 3xy. Again in that we put x is 1, y is m, so it becomes minus 3am. Remember, this is a working rule to find oblique asymptote. We get phi 3m, phi 2m, then phi 3m we know is 1 plus m cube. We differentiate that with respect to m. Derivative of 1 will be 0, derivative of m cube will be 3m square. So we have found out derivative of this phi 3m, that is phi 3 dash m. Now to find m, see what we have to do, we have to equate this phi 3m with 0. Phi and m in general we have to equate with 0. So 1 plus m cube is 0, m cube is minus 1, so minus 1 can be written as cube of minus 1, so m becomes equal to minus 1. Taking cube root on both sides, we'll get m is minus 1. See, we can solve this equation in different way. We can get 3 roots. See, even if you solve it on calculator, we'll get 3 roots. 1 will be real, 2 will be imaginary. We are considering only the real root, minus 1. Or in this simple way I have solved, m cube is minus 1. Minus 1 can be written as cube of minus 1. So m cube is equal to cube of minus 1. So it means that m is equal to minus 1. We have found out slope of the oblique asymptote. And now, to find C, we have a formula. C is minus phi n minus 1m upon phi n dash m. In our case, n was 3 and n minus 1 was 2. So C is minus phi 2m upon phi 3 dash m. Phi 2m we have found out just now. We know the value of phi 3m is minus 3am, and phi 3 dash m is 3m square. Minus into minus becomes plus. 3 will get cancelled. 1 m gets cancelled. We get C is equal to a upon m. But already we had found out the value of m as minus 1. Substituting m is minus 1. Here we get C is a upon minus 1. That is C is minus a. So see, we have got slope m of the oblique asymptote as minus 1. Y-intercept C as minus a. Therefore, the equation of oblique asymptote is given by y is mx plus c. We know. In place of m we will write minus 1. In place of c we will write minus a. We get y is equal to minus x minus a. Bring all terms on one side of the equation. On the RHS, we'll get x plus y plus a is equal to 0. Now, so this is the required oblique asymptote. Now to draw that, see, this is our x-axis or y-axis, the origin. And see, to locate this line, x plus y is equal to a, the oblique asymptote. If I prepare this table, if in this, if I put x is 0, in this equation, if you put x is 0, we'll get the value of y is minus a. If you put the value of y as 0, you will get the value of x as minus a. So see, we know that 0 comma minus a is a point on the y-axis and it will be below x-axis. Y is negative, so it should be below x-axis. And the second point minus a comma 0. Here y coordinate is 0, that means it must be on the x-axis. Remember, on y-axis x coordinate is 0, on x-axis y coordinate is 0. We get these 2 points. So we have drawn a line through this. So that is our line, x plus y plus a is 0. So that is the required oblique asymptote. So the curve is going to run parallel to this line. So see, we have just discussed how we can find a oblique asymptote in case of implicit relations. Then yes, the next important point is to find the region of absence, or I have short formed it as ROA. So see, we find what is the region of absence. That means where the curve is not present. So that automatically we'll also get the region of presence or the region of existence, the region where the curve is present. Now to find the region of absence, first we express the given equation in the form y square is f of x. First express the given equation in the form y square is f of x. Now the region where y square is negative is the region of absence. जिस region में y square negative आएगा वो region of absence हो जाएगा. Because see, if y square is negative, suppose for example y square is minus 1, y becomes root of minus 1, which becomes imaginary. Once you get minus inside the root, it becomes imaginary. So see, to find the region of absence, first we express the equation in the form y square is f of x. That means we bring y square on the left hand side and all the terms of x on the right hand side, and then we try to identify the region, or we try to find the values of x for which y square is negative. So the values of x for which y square is negative, or the region where y square is negative, is the region of absence, and the region where y square is positive will be the region of presence or region of existence. Now see, for example, let us see this example of this equation: y square is equal to x cube upon 2a minus x. So this is the given equation which we have expressed in this form. Y square is f of x form. So we have y square on the left side and all remaining terms of x on the right hand side. Now see, just observe that numerator of this equation becomes 0 when x is 0. If you put x is 0 in the numerator will be 0 of this equation. So I have drawn that line x is 0, that is y axis. You can see that the denominator becomes 0 when x is 2a. If I put x is 2a in the denominator will become 0. So I have drawn this line x is 2a. So we know x is 2a is a line which is parallel to x is 0, that is line parallel to y axis, and since it is positive we have drawn it on the right hand side of y axis. So see, I have drawn these two lines, x is 0 and x is 2a. So I decided that I have to draw these two lines. I saw for what values of x either this numerator or denominator is becoming 0. Numerator is becoming 0 for x is 0, denominator is becoming 0 for x is 2a. So we draw these two lines. What is the use of drawing these two lines? These two lines will divide the given region into three parts. Which three parts? The first part is x less than 0. If x less than 0 means x can be minus a, minus 2a, minus 3a till x is minus infinity. So x less than 0 means x is negative value. It can be like minus a, minus 2a, minus infinity, etc. Then the second region is the region between x is 0 and x is 2a. The region between 0 to 2a means x can be 0.1a, 0.2a, 0.5a, 1.5a, 1.9a, etc. So those are the values between x is 0 to 2a. And the third region is x more than 2a. X more than 2a means x can be 3a, 4a, 5a, x is 5a, x is 7a, x is infinity. So x greater than 2a will cover all that. Now, whatever is the region of presence or region of absence, has to lie within these three parts or these three regions. For that, what we do, we consider some value of x in each of this region, and we see in which region y square is positive or in which region y square is negative. The region where y square will be negative is the region of absence. Like for example, if you consider this first region, x less than 0, assume any value of x which is less than 0. Like for example, I have considered x is equal to minus a. See, I assume x is minus a. You can take any negative value of x, like x is minus 2a, minus 3, etc. I have taken x is minus a. This value of x I am going to substitute in this equation, and I will just check whether the given equation, whether y square will remain positive or negative. See, if I put x is minus a here, y square will become cube of minus a upon 2a minus of minus a. Be minus a cube upon 2a, minus of minus will become plus. We get minus a cube upon 3a. So see, observe that if you substitute x is minus a in the numerator becomes negative, whereas if I put x is minus a in the denominator becomes positive. So negative upon positive will be negative, y square is negative, so therefore this is region of absence. The curve is not present here, curve will not be present here, it will be a region of absence here. Curve will not be present in this region, x less than 0. Similarly, now if you consider the second region, that is region between 0 to 2a. In this region between 0 to 2a, you consider any simple value of x. Like for example, I have considered x is a. You can take x is a, x is 0.5a. Okay. Remember, this we are doing just to check whether y square is positive or negative in that region. If I put x is equal to a in this equation, the numerator will become a cube, denominator becomes 2a minus a, that is a cube upon a will be a square, y square is a square, we are getting positive value of y square, so it is a region of presence. The region where y square is positive is region of presence. Now the third region, x more than 2a, we can assume any value of x more than 2a, like I have assumed here x is 3a. For example, I have taken x is 3a, that if I put it here, cube of 3a will become 27a cube. If I put x is 3a here, 2a minus 3a becomes minus a. you can observe that numerator is positive, denominator is negative. Positive upon negative will be negative. That is the region of absence. Remember, our aim is to check whether y square is positive or negative. Region where y square is negative, like here y square is negative, so we say it is region of absence. We are not interested in the magnitude here. We can do this part orally also. I have shown this for our understanding. Remember, if y square is negative, it will be region of absence. So here this portion x more than 2a is region of absence. The curve will not be present here. It is not existing in that region. It exists only in this region 0 to 2a where y square is positive. Also, see, sometimes it may not be possible to express the equation in the form y square is f of x. In that case, we express the given equation in the form x square is some function of y. We'll bring x square on the left hand side and all remaining terms of y in the equation on the right hand side of the given equation. Now, the values of y for which x square is negative is the region of absence. The region where x square becomes negative will be our region of absence, whereas the values of y for which x square is positive is the region of presence. The region where x square is positive is the region of presence or region of existence. Now, we'll consider example. Suppose we have an equation x square is equal to y cube into 2a minus y upon a square. This is suppose the given equation. Now, see, observe that I have brought x square on the left hand side, all remaining terms of y on the right hand side. First of all, we see for what values of y either the numerator or denominator becomes 0. Now, in this case, there is no term of y in the denominator. In the numerator, it is y cube into 2a minus y. So, see, we can see that the numerator will become 0 when y is 0. Y is 0 means it is nothing but the x-axis. It is this line, x-axis. Numerator becomes 0 for y is 0, that is the x-axis. I have drawn the x-axis. Then again it becomes 0 when y is 2a. If I substitute y is 2a in the numerator, 2a minus 2a will be 0. Numerator becomes 0. I have drawn this line y is 2a. Remember, y is 2a is a line which is parallel to y is 0. That is parallel to x-axis. And since y is 2a, it will be above the x-axis. So remember, we have drawn these two lines, y is 0 and y is 2a. I saw for what values of y the numerator or denominator becomes 0. It becomes 0 in this case. The numerator becomes 0 for y is 0 and y is 2a. So that's why I have drawn these two lines. Now, what is the use of drawing these two lines? These two lines will divide the space into three parts. And in these three parts, in some part it will be region of absence or somewhere it will be region of presence. Now, to decide that where it is region of presence or where it is region of absence, we are going to substitute some values of x in the given region and check whether x square is positive or negative. Wherever x square is positive, it is region of presence or region of existence. Wherever y that x square will be negative is the region of absence. Now, see, the three parts which are formed by these two lines are first of all y less than 0, y less than 0. Second is the region between y 0 to a, region between 0 to 2a, and the third region is y more than 2a. Now, in each region, we consider some value of y. Like suppose for y less than 0, if I consider this as the first region R1, y is less than 0, the region below x-axis, where y will be negative, like y is minus a, minus 2, etc. I have assumed y is equal to minus a. I'll put this value of y in this equation. I'll just check whether x square is positive or negative. So see, if I put y is minus a here, it becomes cube of minus a into bracket 2a minus of minus a. Minus minus will become plus. Simplifying, you will find numerator becomes negative and denominator remains positive. So negative upon positive is negative. X square is negative, so it is a region of absence. If x square is negative, it is region of absence. Similarly, if you consider the second region, that is between 0 to 2a, 0 less than y less than 2a. So that is the region where y will have values between 0 to 2a, like 0.1a, 0.2a, 0.5a, between 0 to 2a, 1.5a, etc. Now, if we take any simple value of y, say suppose for example y is a in that interval, and put in this equation, we'll get x square is equal to a cube into 2a minus a upon a square. Simplifying, it comes out as a square. So that is the, we can get x square is positive, x square is positive, so it is the region of presence. The curve is going to be present there. Then consider the third region. Third region is y is greater than 2a. So that is the region above this line y is 2a. So it can be y is 3a, y is 4a, etc. till y is infinity. We consider some simple value of y, say y is 3a. We put that in this equation. Put y is 3a, so we'll get x square is 3a cube into 2a minus 3a upon a square. 2a cube will be 27a cube, which is positive. 2a minus 3 will be minus a, negative, upon a square. You'll find numerator becomes negative, denominator is positive. So x square becomes negative. X square is negative, so it is a region of absence. So this is going to be a region of absence. So the given region was divided in three parts by the two lines y is 0 and y is 2a. We saw in two regions, for y more than 2a and y less than 0, it is region of absence, whereas between y is 0 to y is 2a, it is region of presence. Now, after finding oblique asymptotes, we can check whether there are some special points on the curve. So we check whether the given curve cuts the x-axis or y-axis or any axis of symmetry for the curve. See, first we check, in the first step we had checked whether the curve passes through the origin. We should also check whether it cuts some another point on x and y-axis except the origin, or if there is any other axis of symmetry like y is x, etc. We should check whether the curve cuts that axis of symmetry. Also, if at some special point, suppose a comma b is some special point, if at that point dy by dx is 0, then it means that the tangent at that point a comma b will be parallel to x-axis. So remember, if you get some special point on the curve, in general, suppose if it is a comma b, then we should find dy by dx at that point. And if dy by dx at that point is 0, it means that the tangent at that point must be parallel to x-axis. It is important to find tangent because tangent decides the nature of the curve. Like, we'll come to know how the curve is going to take a turn. So for that, we should find dy by dx at least the special points. Then, if at some point a comma b, if at some point, some special point a comma b, if dy by dx is infinity, then it means that the tangent at that point must be parallel to y-axis. So if dy by dx is infinity, means that the tangent at that point must be parallel to y-axis, or if that point is on y-axis itself will be tangent to the curve. Now, if necessary or if possible, we can prepare a table of values of x, y and dy by dx. So suppose at some point x is a, y is b, we can find what is dy by dx. We can mention that by preparing a table. Yes. Now, yes, one more last rule we can see that if there are 2 points of the curve on any axis, if there are 2 points of the curve on any axis, x-axis, y-axis or any other axis of symmetry, if there are 2 points of the curve on any axis and the curve does not exist on either side of the 2 points. So if there are 2 points on the curve and it does not exist on the either side, that means it is not existing either on the left hand side of that point or right hand side of the point or on both the sides, then there is always a loop between the 2 points. See, if there are 2 points on any axis and if the curve does not exist on the either side, it ceases to exist on either side, then there must be a loop between the 2 points. Now, for example, if you consider this example, a square into y square is x square into bracket 2a minus x into x minus a. In that case, so suppose we are just trying to see where we get a loop. So suppose this is a given equation, a square y square is x square into 2a minus x into x minus a. Suppose we have checked the symmetry, we know that it is symmetric about x axis because there are only even powers of y. We know that the curve is not going to pass through the origin. In this case, the curve will not pass through origin. We have found out region of absence and all that, and we can see that the curve passes through the point a comma 0. If you put x is a, y is 0, put x is 2a, y is 0, so the curve passes through these 2 points a comma 0, 2a comma 0. And after finding region of absence, we have found out that the curve does not exist for x less than a and it does not exist for x then more than 2a. In simple words, see, after, like, I am showing the last step directly, I am just showing the application of this rule, that if there are 2 points on any axis, like here in this case there are 2 points on x axis, a comma 0 and 2a comma 0, and the curve is not existing on the right hand side of the point 2a comma 0, it is not existing on the left hand side of a comma 0, then it means that there is a loop, there is a closed curve between these 2 points. So that we are drawing approximately. Also we can find what is the tangent at a comma 0 and 2a comma 0 to decide the nature of the curve. So you will find in this case, if you find dy by dx at these 2 points, you will find dy by dx at these 2 points is infinity. That means at point a comma 0, the tangent is parallel to y-axis. Also here the tangent must be parallel to y-axis. In general, if there are 2 points on any axis and if the curve does not exist on either side, either both the sides, left hand side and right hand side of those 2 points, or say at least one side, if it is not existing, then it will be a loop. Like in this example, you can see, so this curve y square into 4 minus x is x into x minus 2 the whole square. See, if you check, you can see that when x is 0, y is 0, the curve passes through origin. When x is 2, y is 0, the curve passes through the point 2 comma 0. After applying all the rules, you will find that the curve does not exist for 0 comma, does not exist on the left hand side of this origin, or it does not exist on the left hand side of y axis, but it exists from 0 to x is 4, and there are 2 points 0 0 and 2 comma 0 on the x axis. So see, the curve passes through these 2 points 0 0 and 2 0 0 2 0, which lie on the x axis, and the curve does not exist on one side. Therefore there must be a loop between these 2 points. So in such case we can get a loop. So the curve may not exist on two sides of those 2 points, or it may not exist on any one side. In that case there will be a loop between the 2 points which are lying on the same axis. So this is how we can trace the curve using these rules. See, revise these rules. These rules are important. The first time when we read the rules or listen the rules, we may find it difficult, but after practice we certainly understand. So if you follow the upcoming lectures, we'll be discussing the problems based on Cartesian curves right from start to end. So right from how to check the symmetry till how to draw the curve. So keep watching. Thanks.